All right, so hopefully we're recording what you have over there. So basically, last time we started this problem, basically here we're doing the wing spars, which are tapered. So basically tapered means what? That you see the width over here is not the same as the tip, and the height is about the same thing over here. So the process is the same thing. In this problem, I think we needed to calculate that at 2 meters from the end section. So right in the middle, we make a cut. So in the middle, we have what? It will be, because it's linear, the height, instead of being 0.8, will be what? 0.6, no? Same thing for the width. So we have to calculate the moment of inertia at this cross section. First we needed to calculate the loading. So we know the shear will be constant. We know the moment will be 0 at the tip, maximum at the root. So right in the middle was just the value of 200. So that's the loading. Then we calculated the moment of inertia in order to be able to calculate the stresses. Okay. That's case 2, I think, of the approximation. And from here on, basically we find the stresses. With the stresses, we can find the value on the stringer, the PZ component, using this equation. Then because of the geometry, this is the factors of the taper on the X and the Y along the length of the beam. So we did all this stuff. Then we need to find what is the value of the PZ. Then we completed this table. And with this, we need to find out of the external force, how much of the shear force is being carried by the flanges or the stringers and how much is being carried by the panel, no? Now that we know how much is carried by the panel, which is this value here, we did this. To simplify the equation, we neglected this term over here. Okay, we just use this one. And I think that's where we started doing this. We made the cut between 6 and 1. I mean, correct me if I'm wrong. We give you these values. We did all these values, and this is where we stop, no? Is that correct? So now what is the next step we need to do? Next step is to do what? Since we made the cut, meaning that here is 0, we're going to have one internal shear flow. Okay? I think we did it a bit more. I think we did this, show the internal shear flow, and I think this is where we stop. So this is the same procedure. Then we took the moments about, here, point O, okay? And please let me know where is the last thing I wrote. Did we write these lines over here or not? We should have a plus. Yeah, this one here, plus 2AQ sub 0. We just did not calculate this. But did we write that equation or not? Okay, so if you want, did we say what the area would be? It would be the whole area, no? Since we are doing around. So basically, if you want, I would just copy what you see on the board, and then I will take it from there. We can do the last stage together. I mean, I can just show you since it's on the screen. So if you solve for Q sub naught is 76.39 newtons per meter. And what should be the last step? Now you need to add this value to the Q12, Q23, and so on, no? To the Q bar values. Oh, you open here. No, that's not what I want. Okay. Do you need more time for this page? Okay, if you want, maybe I can scroll down. And basically after this, oops. Basically what you need to do is only add this value. Okay, so it looks these 2 pages. You need to add these values to these ones over here, to the previous ones that we had. Why is it not going down? Because the page. So you can just copy the last. What just happened? What did I do wrong? Can you help me here to put the view? What's here? Okay, how can I change the zoom over here? Can you see that? That view over there?
To the left.
So my left or my right?
Which? Go to the windows.
One more.
One more because
Yeah,
you know
that's
different. This one. Okay, now
Zoom, go to zoom.
is that zoom?
No, go up. One more. Goes. Oh no, go down. Go down about 1 foot on the screen. No, half foot. No, down half foot. Down a foot. Keep going. One more. There you go.
I click over here?
Yeah.
All right. So basically, if you want, you don't have to copy these values, just want to make it a bit faster. This is at the end, the final distribution on the panel at that section. Okay, so I'm preparing an assignment, which would be to redo this. I mean, not this problem, but similar problem, no? And might be a bit more tedious because actually it has a force, a shear force in both directions. These ones are not symmetric if you look at it because they changed. I mean, like many of the assignments that I'm doing, maybe, I mean, I told some of you is they come from Dr. Radostas, AE418. So same problems, but we solve them slightly differently. I mean, basically, this is the same process. What happens is that the tedious part over here is that you need to find out how much of the shear force is supported by the stringers and how much is being supported by the panel, no? Okay, and because it's a change in taper, you need to find out how much is being carried by each one of the stringers then, which is the tedious part. After that, it's basically the same thing we have been doing over and over. So let me re-explain this very quick. So somebody had a question, why sometimes I use the Q bar and sometimes the Q, and just say for this equation or any other equation, you see the Q bar already contains the Q sub naught, but the Q's do not contain the Q sub naught, and this is the reason. So if you take the moments, if you consider only the Q's, you need to add at the end the effect of the Q sub naught, but if you use the Q sub bar, the effect of the Q sub naught is already included. Recording.
I just put another piece of paper next to what you're drawing, so low as
Another piece of paper like this.
Yeah. Well, not like covering. Because the black is.
Oh, it's doing the contrast, you said?
Yeah, so if you have more white on the page, it's gonna lower the brightness.
Is that better?
Yeah.
Okay, yeah, I don't mind doing that. No problem. Okay, so basically what we do first, the sketch of a wind box. So hope you can do a better picture than me. So basically, like I said, you need to do a box. All right. Okay, let's say this box. You break it into two sections. Okay, so this length is 500 millimeters. Other distances will be in millimeters. So this is 500, 500. The height is 200. Okay. Ooh, and there's something here. I think we have an, and here the T is going to be a force Vy being applied equal to 2000 newtons and a shear force and a torque of 1,000 Newton meters. Being applied counterclockwise over here, so it's positive. Okay, so this will be, if you want, this one will be known as Bay 1. This is not that important, but let's put it over there. And now comes the important piece of information is that, so this is a wind box. This will be all different parts if you want, or they can be welded. But over here, we're going to remove, so let's say top panel is removed. Okay, so what is that going to do? That's going to affect something, no? Structurally. 61. Do you visualize what's happening over here? And the width over here, this is 400. Do you visualize this? It's a box with panels, okay? With two bays, and then you remove the panel, the top panel of the first bay. Okay? All right. So let's say here I'm going to say Vy is applied at the shear center. What does that imply? What was happening at the shear center? The other way around. There is no torsion. So basically it will be pure bending at that point. So basically, if you look at it would just be moving up or down at that point, no? Due to the Vy. So this apply at the shear center. So we mean Vy does not induce any torque. Does not. Thank you. Yes. Yes, the height is 200. This is the height is 200, the width is 400. Okay, so that's it. So let's see what's happening. What we need to do is determine the shear flows in the panels and the load distribution in the stiffeners, or what this is kind of what we did on the slash flanges. It's kind of similar to what we did at the beginning. If you remember the wind box, when we say the force, the stiffeners need to sustain the force in one direction, and you need to find the shears. It's basically the same thing, but a bit more complicated. Okay, so what is the general procedure to do this? Let's see if I can keep the contrast. Okay, this is the way I like to do it. So 1, study for Vy only. You find the shears due to the Vy only. Then 2, similar, but say study for T only. And 3, using superposition principle, add solutions from 1 and 2. So this is kind of the, not this assignment, the previous one asked to study the load separately and then to add the effects, no? When you use the term superposition, what are you implying? When can you use the principle of superposition? Correct, but even if it wasn't determined, but basically, for example, if you have the function x squared, can you add the solution of both of them? I mean, basically what I'm trying to say is that you can only use the principle of superposition because you're assuming that the solution is linear, no? It goes through a straight line. If it wasn't going through a straight line, then you will not be able to do that. Okay, so that implies that our solutions are being linear. All right, so we're going to do part 1, which is we're just going to study the shear force Vy equal to 2000 newtons only. Okay, so we say here bay 2. We're going to start at bay 2. Let's say the tip at the end. Okay, so that means we will be in this section over here. So let's maybe put names here 1, 2, 3, 4. That way we know where we are. Okay. So let's say I'm here. So I'm going to do a little figure over here. So one, 2, 3, and 4. All right, so we look something like that. We say this is going to the shear center, so I'll just make it in general here, going up. Okay, so now you remember, what did we say at the beginning of the semester is that if you have a force, only the members that will be on the same direction of the force will be resisting the load. Yeah, so in this case, let's say we only have panels. So what will be the panels which are in the direction of the load? It will be the 2 side panels, no? This one over here and the one on the other side. Okay, so here it doesn't matter what is the assumption you do. If you want, we can say this will be Q. So we can do this one up, down, and this one will go this way, and this one will go the other way. This will be our Q1 on one side, and then you will have something similar on the other side. Q1, and remember, you asked me here, the height or the depth here is 200, and this is both are Q1, correct? Because you assume they're both going to resist the same amount. No, the force applying to the shear center will be pure bending. just going up, no, pure bending. So both sides will be resisting the same. Okay. No, that's a very good question. This is how to do this process is understanding. Okay, so let me write it down if you want. Only the members or the panels in the direction of the load are resisting the load. So in other words, I'm still going to do another small figure, no needed, but if I simplify this figure, we have basically here Dy, we have over here Q1 and Q1. Okay, something important here that I want you to notice is that when the load is due to a shear force, what is the assumption that we do for the shear forces? This one, no? Yeah? Okay, because you're going to see what happened now in a minute. Okay, so this is 400. How do we find the value of Q1? Okay, so if you want, you can do summation of forces equal to 0, or you can do external, internal, but this is really internal. So we do Dy, so they're both going up, plus 2 Q1 times what? Was it 200? Oh, here I put 200 and then I put 200, so it should be 200. 400 was the width. So 2 Q1 times what? 200 equal to 0. So from here, you can solve for Q1. That will be equal to minus Vy over 400, which will be minus 2000 over 400, which means that Q1 is equal to -5 newtons per meter. So if it's negative, then what does that mean? It's going the direction, so basically we'll be going, let's see, this way here. Okay. Okay, so let's see that. That's a different page. So where is my first page? Oh, here it is. Okay. So what would be the shear distribution in this panel, in the one in the middle? Yeah, what is your question?
So my question was, Dy wasn't at the center, would there be a shear flow in the upper and lower panel?
No. I mean, yes. What happened is that if it wasn't on the applied the shear center, it will produce a torque. Correct? Then the torque will be should be resisted by all the panels, no? Is that a question? But basically now, okay, so we calculated what's happening here in this panel, 1, 2, 3, 4. Because the Vy is 2000. What will be the distribution here in this panel in the middle? This one, which is right in the middle. Will it be any difference? What will be the value of the load in this panel? Be the same, no? Okay, so if this panel was also resistant, it should be the same as this one, no? Okay, so maybe let's talk about the load for a second. So let's see, loading. maybe it's important to do the figure, is that if we look at the shear diagram, if you want, so let's say this is Z, the middle of the panel is 500, so let's say this is bay 1, bay 2. The value of the shear is constant. Okay, this is the, let's say, 0, 500, 1000. So, I mean, again, you can do it. Let's do the details, but so that will mean now, if we look now at this panel over here, okay, maybe you want to call it whatever, 5, 6, 7, 8 to make a difference. Okay, so I'm just going to redo the same panel. We can do the same thing for exactly the same procedure, but I'm going to go a little bit faster. So let's say here for the panel, how did I call it? 5, 6, 7, 8. Basically, we know the value of the load is still the same. And maybe, let me do this again. Okay. Same figure as before. And basically here, I mean, we know it's going to be same as Q1, but let's call it Q2. Okay, same thing on the other side. Q2. Or we can redo this as same figure as before. Q2. Q2. 200. dy. So as before, we just do summation of forces. I mean, it's identical as before. This will give what? Vy plus 2 times Q2 times 200 equal to 0, which will give Q2 equal to minus Vy over 400 equal to minus 2000 over 400, which means that Q2 equals Q1 equal to negative 5 newtons per millimeter. And again, if you want, you can just do this figure here. Oh, sorry. Basically, it's exactly the same thing as before, but that was expected, no? Yeah, I just call it differently and show you that it's the same. Instead of 10 years, the same value. Okay. Okay, so now what will be the shear flow on the top panel, lower panel, and the lower panel of bay1? 0, no? Okay, so if you want, you can write over here this one. So shear flows in, let's say top, bottom, of bay 2 and lower panel of bay 1 are 0. Why? What is the assumption we are doing? They are not resisting the load, no? They're not resisting Vy. And that's because of the assumption that we made from the beginning is that only the members in the direction will be resisting the load. Okay? Okay, so now we are done with the shear. So now let's find next. Let's find the forces in the flanges. So maybe let me keep using numbers since I started using numbers here. 5, 6, 7, 8, 9, 10, 11, 12. Okay, so let's say here, I'm just going to do one. Let's say I'm just going to do the flange of the stiffener 951, okay? All right, so let's look over here, flange slash stiffener 951. So before we do the calculations, let me ask you a question. If we just consider the force Vy, the top, should it be in tension or compression? The top would be in compression. The bottom, tension. So 951 would be, that member would be in tension or compression? Tension, no? Okay. Just to know about the sign. So let's say this one would be in tension. Okay, next I'm going to do here a figure of the plan. So let's say this would be 9, 5, 1. This should be 5 should be right in the middle. I didn't do a good job. So this is 0, 500, 1000 the distance. Okay, what should be the load at the end? What should be the load over here? Oh, sorry, at 1. Remember, now we're looking at the flange. So this one is only has load on the axial direction, no? So where will it be maximum? At 1 or 9? I mean, it's the same thing that we did with the first type at the beginning of the semester. Okay, what would be the load maximum here? This is cantilever, no? I'm not talking about the shear. Now I'm talking about, yeah, okay. Let's do that if you want. So basically, if you look at the distribution here that we have, in one direction should the distribution be going? You look at this, it goes in the opposite direction. So we made it go from whatever. 6, so it's going from there to there, so it's going to go in the opposite direction. I know we're looking at the bottom, no? So it should be going, this is bay 1, so it should be going in this direction, no? It was the opposite direction here, so we go in the opposite direction than this one, and this one will be the same thing. So basically, this was the Q2 here, which now I just use the magnitude because I already did on the correct direction. So what I was trying to say before, what should be here the actual load here at 1? Here is going to be 0 at the end, no? Just like we did before. What will be the load at 5? This is 500. This is 500. What will be the load at 0.5? What is it? How much is 500 times 5? 500 times 5. 2,500. And then at P9, what would be the load? $5,000. Another 2,500. So basically, if we needed to do a plot here of P, we say what's being tension, so we can leave it positive. What will be the distribution in that flange? It will be here, let's see, will be at 0. $500, 1,000 would be 5,000. 2,500 and 0. Okay, and because we are looking at the lower one will be in tension. Does that make sense or not? Okay, this is the way I will do it. Now I'm going to show you a second way to do this, but just because it's also done in different textbooks. So, okay, but I think this is my favorite way to do it. It's simple, nothing strange. Okay, and alternate approach to find the load P in the flange is. And again, it's very simple stuff, but okay, we need to do it. So let's say here we are at the wall. Oh, I put. Okay, we don't need to do that. I just need to look at my figure again, the number. Okay, here we go. All right, so we are here at the wall. I mean, for this, it really doesn't matter, but okay, so basically we're talking over here about points 9, 10, 11, and 12. Okay, we say over here that because the way of the load, the bottom will be in tension, the top will be in compression. Okay, so if I look at the load along these stiffeners, If the top is in compression, what does that mean? That is going in, so this will be P. And if it's in tension, it means that the load will be going that way. All right, so here, let's take a point A that will be right in the middle. And that way, we have that distance is 200. That distance will also be 200. The height would be 200. Okay, so now this is the hard part to visualize if you want. So now all these loads over here that we over here showing will be creating what? These two loads here are creating what? They are creating a torque about this axis over here, no? It's actually which is going to make it bend, correct? Okay, so if you look at it, the understanding is that this force over here is creating bending to the top. How is it creating bending? By having these axial forces that go in the opposite direction. So they're going to create a moment about this point, no? Along this line. Yes, about this line. Okay, so you can do it in any direction that you want. Let's say I plot it under this form. It's called this moment created by the forces P, M. Okay, so basically, if I apply here summation of moments about point A equal to 0, what should I get? So the moment M, no? And now these ones are creating a moment on which direction? Will be on the, it looks like it's going to go rotate that way, no? So it's going clockwise. So that would mean that this will be creating a moment of how much? Or you can do P, each one at a time. So it would be P times what? What would be the distance between P and the middle over here? It would be 100, no? Yes, this is 200. So this force will be created a moment P times 100, P times 100, P times 100, P times 100, no? It would be 4P times 100 equal to 0. So from here, we could find that P would be equal to M divided by 400. All right, so maybe I should have done that at the same time as the shear. So similarly, we did this over here for the loading, for the Vy. We can do the same thing for the moment. Okay, so let's look over here, loading, looking at the moment. All right, so we don't need to do too complicated, but what would be the moment created by Vy? What would be the value of Vy at this point over here, at point A, which is right in the middle of the panel, 9, 10, 11, 12? It would be Vy times 1000, no? Yes? Okay. So if you look at it, then here we'll have Vy times 1000. What would be the value at here at the middle would be Vy times 500. And what would be the value of the moment at this panel 1, 2, 3, 4? 0, no? Okay. So basically we can say we'll go from here we have 0. Here we're gonna have what? 2000 times 1000. Here would be what? 2000 times 500. Okay, so this would be what? 2, 10 to the 6. The M. So what is the value of M at the panel 9, 9, 10, 11, 12? Where is that panel located? Located here at the wall, no? Yeah. So what is the moment over here? What will be the value? Will be 2, 10 to the 6 newtons millimeter. Okay, so substituting. So if we did that correct, what should be the value that we get at the P? What should be the value at P at here at 0? P 5,000, no? So it's a matter of double check. So it will be P equal to M divided by 400, which will be 2, 10 to the 6 divided by 400, which, if we did everything right, should be equal to what? 5,000 newtons, no? I'm pretty sure, I mean, 20 divided by 4 is 5. It will be 5, 10 to the, so 0.5 10 to the 4, which is 5,000, no? I mean, I think the other method is simpler, no, than this one. But this one implies a bit of understanding of what is happening. Any questions so far? No? Okay. So that's it for this. So here we are done with studying the load for Vy only. Now we need to study for T only. Two. Study for T equal to 1,000 Newton meters only. For the torque? Yes. Are we talking about let's go back to the figure. Oh, it's 1,000 Newton meters, correct. So let me double check. I didn't pay attention to that. Let's go back to the, on my figure here, I have 1,000 Newton meters. So it will be 1,000 times 1,000 Newton millimeters. Okay. Oh, a good question. I mean, it's right. Okay, so since we're talking about this, let's look first at the loading. So that loading. So again, is 0, 500, 1,000. If you have a torque being applied at the tip, what should be the value of the torque in the panel 5, 6, 7, 8? The same. And what should be at 9, 10, 11, 12? The same. Okay. So basically, it's like the shear. We can say that the torque would be constant over here. Okay. Which is 1000 newtons. Okay, so in order to do this, we use something which is called reverse bending. Okay, many times called reverse bending. So let's see. I'm going to go at bay 1. Okay, so basically, I'm going to do here the panel again. It must be 4. I'm still going to do point A over here. So this will be our points 9, 10, 11, 12. I don't want to put too much. Okay, the torque T will be about which axis? It's not the same as before, no? The torque is going to make it twist in that direction, no? Correct? So the torque is being applied about the Z direction. You've always been using what? The X, Y, Z. So the torque is being applied between, so this moment here on the previous page, this moment, what about which axis? What's this one? About X. Perfect. So let's put maybe add the X over here. It might be, it might help for the understanding. MX, MX, and this will be MX. All right. Now that we're applying the torque is about which axis? About the Z axis, okay? So if you want, if I do here now the figure, let's say it would be T is about the Z axis. Okay, Z axis is what? Again, this will be 200. So now, why is this called reverse bending? So in here, let's say we're going to call on this side here. So how do we call the shear flow in this panel? We call it Q, no? This was Q1, this was Q2, no? Okay. So this one, I'm just going to call it on this side. Now, let's say it's going to go up on this side. We're going to call it Q to make the difference, Q bar 2. Okay, so if this is doing the torque in that direction, basically we know that the shear flow inside need to go and counter-react this one, no? Yeah, so this one should be going up. In this one will be going what? Up or down? Down, no? Because the torque. So this will be Q bar 2. So if I do it this way, now we do what? Summation of moments about point A, or the summation of the torque, okay? Will be equal to what? T Then this 200 over here is going to create a clockwise moment, no? Of what? 200 Q bar 2 will be the value of the force. What would be the arm? I didn't put it before, but what should be the arm? This was 400, no? So it's right in the middle, so that will be times 200. The other side will be doing the same thing, so minus 200 Q bar 2 times 200. This should be equal to 0. Yes. Just randomly. Just like that. Right. Basically, what I did is such a way that they will go in against the door.
Okay, that's
Okay. Does that make sense? But mathematically, you could apply them, you could pick them in any direction. The math will give you the right sign at the end. Okay. But if you look at it, the way I like to see at the problem in the structure is that the internal, I'm going to counter react whatever is coming from the external load, no? Okay. So if you do this, then what do we get? That we can solve for, so let's say we have T minus 200 squared. That's maybe not a very smart way to factor out, but Q bar 2 plus Q bar 2 equal to 0. So basically what I'm trying to solve here is for what? For Q2, so it will be Q bar 2 will be equal to what? Will be equal to E divided by 2 times 200 squared. And good you asked that before, because otherwise maybe I was going to do a mistake. What is T? T is 1000 Newton meters, which will be what? 10 to the 6 newtons per millimeter, no? Okay, so that at the end we can say that Q bar 2 will be equal to 10 to the 6 divided by 2 times 200 squared. And if you take your calculator, what I get is that Q bar 2 is equal to 12.5 newtons per millimeter. Okay, so now we are left with what? So we study let's see if I can put the mouse over here. We study everything for Vy only, and we calculate now, because what's happening here is that on the bay 1, the top panel is being removed, no? Yes? So basically, what we are doing in this figure is assuming what? That only the side panels over here I cannot resisting the torque in that location, no? Okay, but now if we move to this location, to this bay over here, the whole 4 panels should be resisting the torque. All right, so we have a shear flow in addition to the side, we should have a shear flow at the top and the bottom, no? Yep. So we only have 5 minutes left, so 5 minutes left, so I'm going to stop over here, but this is what we'll be finishing next time. Okay, here the important part for me is that, do you see what is happening? You see, it's nothing mathematically complicated. is everything about the understanding, no? On how to apply the laws. Okay, so I will stop the lecture over here for today.